In this section, I'm gonna cover concave mirror and converging lens. This problem is taken from OpenStax Chapter 2, number 118, and I revised the question by changing it from the back of the lens to in front of the lens. So this is the question, and I defined the question with a diagram. So in this diagram, I define every notations I used, and the problem is asking me to find the location of the final image, to determine the orientation, whether it is upright or inverted, and to determine the magnification, which talks about the size. And since there are two reflection and refraction, one from the mirror and one from the lens, we expect that we have two images. The first image form, it becomes the object, and then the second image form. So as we look at the diagram, the mirror comes to first of the contact, so we consider the mirror first. So let's assume that it is a thin mirror, so I could use the thin mirror equation, and the magnification equation also is valid. From a concave mirror, since it is a converging mirror, so the focal length is going to be greater than 0. And for every concave mirror, the magnification, if it is greater than 0, then the image is upright and virtual. And if it is less than 0, then the image is inverted and real. And if the magnitude of the magnification is greater than 1, then the image is magnified. And if the magnitude of the magnification is less than 1, then the image is diminished. And the magnification works for both mirror and lenses. And the image distance, which I denoted as the S prime, when it is greater than 0, the image would be in front of the mirror, and if it is less than 0, then the image would be behind the mirror. So when I apply the thin lens equation, I get the image distance is 100 centimeters, and then I proceed with the magnification equation, I get -4. So the first image from the magnification, we conclude it is magnified, real, inverted. And from the image distance, we conclude it is 100 centimeters to the left of concave mirror. So right here, I used the ray diagram to verify my conclusion. So this is the object with an arrow. And as I follow the parallel ray, so this is the parallel ray, it will go towards the focal point. So following the focal point connecting to the dots, it will ends here, following from the pink line. And the next thing, we will do parallel rays. So parallel rays is this ray right here. It passes through the focal point and to this point, and then it's gonna reflect parallel to the incident ray of the parallel ray. And the last ray, and these two rays converge at one point, which we find as the image. So it's this point again. And with this point, we could find the center of the mirror, which I connect from the both dots here and here. So when it passes through the optical axis, this is the optical axis, then this would be the center of the mirror. And what it means is like the mirror would gonna be like this, and this is the center of the whole circle. And one point noted is after I finished drawing this ray diagram, you could see the image falls with the same side of the object, so we conclude it is to the left and it is real. And then we could see the arrow is pointing downwards for the image, so it is inverted, and it is larger, so it is magnified. One point I missed before is that it is a point source. What it means is that this object would shine ray at different directions. So it could go from here, any directions. So after we form the first image, this is the first image. We take it as a new object. So we proceed by considering the second refracting surface, which is the converging lens. So since it is a converging lens, then we have the focal length greater than 0. And we assume it is a thin symmetrical lens, so we can use the thin lens equation. And as well as the magnification equation. So the magnification works the same as the mirror, except for the image distance is completely reversed. When the image distance is greater than 0, then the image would form behind the lens, and if the image distance is less than 0, then the image would form in front of the lens, since it is a refracting surface, not a reflecting surface. So we apply the thin lens equation. We have the second image distance, and notice that the object distance, I use the new image as the object. So after we compute the image distance, we compute the magnification as well, and we have negative 0.316. And from this value, we conclude that the second image is diminished since it is less than 1. The magnitude of the magnification is less than 1. And it is real inverted and 39.5 centimeters to the right of the lens. So we draw the diagram again. And at this point, we added the green arrows, which we take this as the object and this to be image. So again, we follow the parallel ray first. So this would be the parallel ray, which is parallel to the optical axis. So once it reaches this point, it's gonna connect with the focal point, since it is a converging lens. And when I finish the drawing, I have an image here. No, this is with first ray, so I have to go with the focal ray to consider where my final image is. So since we have used this focal point, we're gonna use this focal point for the focal ray. So I connect this dots and this dots here with the green line. And then when it goes here, it is gonna refract parallel to the optical axis. So the image is here because we have both focal ray and parallel ray. And then the central ray would be from here, which is the center of the lens, to again this point again. So this would be the central ray. Okay. So with this diagram, I finished drawing the ray diagram. We can confirm if our conclusion right here matches with the ray diagram. So the object, we see the image is diminished since h3 is less than h2, which is this height and this height. It is real since it lies to the right of the lens. It is inverted as this is down, as this object is down, and this new image is up. And then it is 39.5 centimeters to the right of the lens. So everything matches. So the final step is we compute the overall magnification, and to compute that, we have to compare the height of the images. So this is the magnification equation for the first image form, and this is the magnification equation for the second image form, and we combine the equation to have this equation. We compute, we have this number, which is h3 equals to 1.264 h1. So since it is positive, so the image is gonna have the same orientation to the original point source, and since 1.264 is greater than 1, so it is magnified. And at last, we look at the ray diagram, or we could use algebraic, which just adds up the distances for the image and the for different lengths. But looking at the diagram is the most direct way, so I use this as the method to compute the final distances of the image. So since this is the image, this is the image, and this is the original object, we're adding this DO or D naught and this green length. So we're adding 50 and 39.5 centimeters. Oh, I should get a notation for this as S2 prime. Oh no, it is S2 prime. Yes, this is S2 prime. So we are adding D naught and S2 prime to have 89.5 centimeters to the right of the point source. So this is an example of combining concave mirror and converging lens.